Hello class. In lesson 2.9 complex numbers, you'll learn how to perform operations with complex numbers. So you're going to learn how to add, subtract, multiply, and divide expressions with complex numbers. Let's first go over what a complex number is. Now the complex number system again is a number that consists of two parts. We get numbers again from the real number system and imaginary system. I know it doesn't seem very logical, and it creates again a complex number. So for example, 3 plus 2i is an example of a complex number, where 3 is the real parts and 2 is the pure imaginary parts. Now the standard form of writing a complex number is a plus bi, where the imaginary unit I, again this imaginary unit I, is defined as the square root of -1. And if a is equal to 0, then if this is equal to 0 and all we have is this number right there, this is referred to as a pure imaginary value, again where b is going to be a real number and I again is the imaginary part to that value there. Now the complex number system again is an accumulation of all numbers possible. So you'll see again that we add a pure imaginary number with a real number to create again this complex number. Now the first thing we're going to go over is how to add complex numbers. Well, to add a complex numbers, we essentially just follow the same rules of adding any polynomial, in this case any binomial. So we can drop the parentheses since we're adding here. We can drop the parentheses and then simplify this by just combining like terms. So we combine the 5 and the 3, which adds up to 10. And we combine the 3 and the, not 10. I'm thinking of the wrong thing here. The 5 and the 3, which adds up to 8. And then the 3 and the 7, which adds up to 10. So we end up with 10i. And this is your answer. Notice that we end up creating again a complex number. Now, if we're subtracting two complex numbers, we want to get rid of the parentheses again so we can combine like terms. But in this situation, because of the subtraction, it's easier to use the definition of subtraction, which is to add the opposite. So if I distribute that negative sign, that's going to guarantee me that the definition. So I can drop the parentheses on the first complex number, and distributing that operation of subtraction changes the sign to these values in the second parentheses to the second complex number, and then I can follow the same rule of adding by just simply combining like terms. So I add the real parts together, which is going to add up to 10, and then I add the imaginary parts together, which right here, because they're different signs, they're going to add up to a -4, so I end up with -4i. So this is how I subtract them. And that just remind me, let me double check over here. Oh, I made a mistake over here because I just realized this is supposed to be a negative and I mistakenly put a plus sign. So that's going to change my answer here. So looking at that problem reminded me that I was supposed to follow my rules of adding a positive and negative number there, which again is to subtract. So I end up having a positive 4i. So that would be 8 plus 4i. So this is the correct answer there. But again, the main idea of adding or subtracting complex numbers is simply combining like terms. You just simply want to distribute this negative sign into the second complex number so we can combine like terms using the idea of adding the opposite. Now, before we go into multiplication, let's talk about the powers of I. Well, I again is defined by taking the square root of -1. That is the value of I. I is equal to the square root of -1. So if I raise I to the second power, that's the equivalency of getting -1 and raising that to the second power, which as a result is going to equal to -1 because the square root and the square are inverse operations of each other. So we are left simply with -1. Now, using that definition for the next one, I to the third power can be broken up into I to the second times I to the first. And well, since I to the second power is equal to negative 1, I can substitute in that for negative 1, I squared for negative 1, and then multiplying it with I, that's equal to negative I. So I to the third power is equal to negative I. I to the fourth power can be broken up into various ways, but if I break it up into I squared and I squared to do identical factors, well, again, I to the second power is equal to negative 1. So here I multiply two negative 1s equaling to positive 1. So I to the fourth power is the equivalency of 1. Now, if I raise it to higher powers, like I to the fifth power, well, if I break this up into I to the fourth power to I to the first, that adds up to 5. 4 and 1 add up to 5. And I could break it to different ways, but if I do it this specific method and break it up into these specific values, again, from the previous answer, I know that I to the fourth power is equal to 1. So this is the equivalency of multiplying 1 times I, which again is going to equal to I. Now I to the sixth power, if I again use 4 and 2, I to the fourth and I squared, again, I to the fourth power is equal to 1. So using that definition right there, we end up multiplying 1 with I squared. Well, I to the second power is equal to negative 1. So if I multiply a positive 1 with a negative 1, that's equal to negative 1. So this is going to be the answer for that value. Now I to the seventh power, using the same strategy, using I to the third with I to the fourth. Again, we know from the definition of I to the fourth that this is going to equal to 1. And since I to the third is equal to negative I, we're multiplying 1 with negative I, so I end up with negative I again. And well, I to the eighth, that's simply I to the fourth again, and I to the fourth, which can simply just be written as I to the fourth to the second power, 2 factors of I to the fourth. And again, that's going to equal to 1 because we're going to, since this is equal to 1, we're multiplying 1 by itself. So 1 times 1 is 1. And this pattern, as you see right here, is simply going to repeat itself for every 4, every powers of 4. So I to the 9th, to the 10th, to the 11th, to 12 is going to repeat. I to the 9th is going to equal to I, because this is going to be I to the 4th to the second power times 1 more I, which adds up to 9. Remember, this right here multiplies to give us 8, and then 1 more, that adds up to 9. And since, again, this is going to equal to 1, let me do it in the right color. Let me color coordinate this accordingly. Since this is going to equal to 1, 1 to the second power is still going to be 1. So we end up only having I, 1 times I. And then again, the pattern just simply continues, which is negative 1, I to the 4th to the second times I to the third. That adds up to 11, which is going to equal to negative I. And then I to the 4th times I to the 4th, or basically I to the third power there. This is going to equal to 1. Since 4 times 3 is equal to 12, there are no more extra factors, and we're going to end up with that. If I split it up, it looks like this. Let me split it up so I could follow the same pattern as I did before. We have I to the 4th to the second, which is going to 8, which is going to add up to 8. And so that means we're missing 4 more i's, so that all of these exponents add up to 12. Remember, this gets multiplied. So that's how we end up with 8. And 8 plus 4 is 12, which again is the same thing what I wrote earlier, which is simply I to the 4th raised to the third power. And that again is going to equal to 1, because we're going to simply multiply 1 3 times. 1 times 1 times 1. So we end up again with the value of 1. And you see again, the pattern just simply repeats. So the strategy for this, if we raise I to higher powers other than 15, we can continue this pattern, all right? Like for 15, we continue the pattern and see what this value is. Or we can just simply do this. Since we know that I to the 4th power is equal to 1, we want to see how many times can 4 go into 15. So if I divide 15 by 4, this is going to equal to the decimal value of 3.25, no, 3.5 3.75. Yes, 3.75. So I know I can split up I to the 5th power to I to the 4th 3 times, which is going to add multiply to 12, meaning that we have 3 more factors of I left over. And again, 12 plus 3 more adds up to that 15. And the reason we want to do this is because, again, this is going to equal to 1. And 1 raised to any power is still 1. So all we're going to be left with is I to the 3rd power. And since I to the 3rd power is equal to negative I, this is going to be our simplified form of I to the 15th. So I to the 15th is going to simplify to simply a negative I. And we do that again with anything higher than that, because obviously we do not want to follow this pattern and then do this until we get to 62. Follow this pattern here until we get to I to the 62. It's easier again to just simply use this definition, knowing that I to the 4th is going to equal to 1, and see how many factors are going to be left over for that. So if I get 62 and I divide it by 4, basically see how many times can 4 go into 62, I see that I'm going to get 15.5 times. So it can go in 15 times with the remainder. So let's see what that remainder is. So if I get I to the 4th and raise it to 15 to the 15th power, that's equals to 60. So that means that the remainder is going to be 2. And that makes sense. 2 divided by 4 is equal to 0.5. So since this is going to equal to 1, we're going to end up with I to the 2nd power. And using our definition of why I to the 2nd power is equal to I to the 2nd power, wrong one, is equal to negative 1. So raising I to the 62nd power is going to equal to negative 1 ultimately. So there's your answer. Now, because I is defined as the square root of negative 1, we use that rule in order to multiply negative numbers inside the square root, negative radicants. So here, in order to simplify the square root of negative 18 times the square root of negative 10, the first thing we need to do is get rid of the negative sign. And again, because I is equal to the square root of negative 1, taking the square root of the negative sign is going to give me I 18 and I 10. I radical 18 and I radical 10. Now I'm allowed to multiply these two numbers together. I'm not allowed to multiply negative numbers inside the square root. I cannot multiply two negative radicands. I can only multiply positive radicands. So I take the I out, I take the square root of the negative value, getting the I, and now I can multiply the two radicands, which is going to equal to the 180. Now multiplying the i's, that's going to give me I to the 2nd power. Now to simplify this, well, 180 can be broken up to the factors of 36. Yes, 36. Yes, 36 and 5. I was just double checking. 36 and 5. So if I break up the value of 180 into the identical to the factors of 36 and 5, 36 again happens to be a square root and this biggest square root. So I to the 2nd power, well, from left to right, let's go from left to right. I to the 2nd power is equal to negative 1. The square root of 36 is equal to 6. And because 5 is irrational, we're going to keep that inside the square root. So our answer here is negative 6 times radical 5 times the square root of 5. So for number 6, again, we follow the same rule. Just to reiterate this, we're not allowed to multiply, again, negative radicants. So the first thing I'm going to do is take the square root of that negative sign, which is going to equal to I on every single one of these. So we have I times the square root of 24 times I and the square root of positive 3 times I and the square root of 2. Now I'm allowed to multiply the 3 radicands. So multiplying those 3 radicands, I am going to get a total of 144. Again, still inside the square root. Multiplying the 3 factors of I, we're going to have I to the third. Now, since I to the third is negative I, again, from this table right here that we just generated, I can replace I to the third with negative I. And since the 144 is a perfect square, that's going to equal to 12. The square root of 144 is exactly 12. And now multiplying negative I with 12, that gives us negative 12I. And here is our result. Now, this definition right here that we used on example number 5, that I to the second power is equal to negative 1, is going to be useful when we actually multiply complex numbers. So here we were just multiplying pure imaginary numbers. Now let's go into examples of multiplying complex numbers. Now to multiply complex numbers, we simply follow the same rules of multiplying basically binomials. We just simply are going to use distribution. And we start by first multiplying 2 into the second complex number. And that's going to give us negative 10 minus 6I. Continuing with the double distribution, we're going to now multiply negative 4 into the second complex number. So positive 20I and positive 12I to the second power. Now, again, since I to the second power is equal to negative 1, I can do this substitution here and replace this I with negative 1. So I'm multiplying 12 with negative 1 essentially. And by doing so, this is going to simplify to negative 12. Again, giving me a real number instead of this number to the second power. This is a number with I to the second power. And because of that, this 12, which is a real number, can be combined with the negative 10, which is also a real number of this complex number, and end up with a total of negative 22. Combining again the imaginary parts of the complex number, that's going to add up to a total of positive 14, since we end up subtracting a negative and a positive because we're trying to combine two different signs. And here is my solution. Now, because again the strategy is very similar to that of polynomials and binomials, we can also use the box method to organize the product of these complex numbers. So creating a 2 by 2 box, I can multiply these two numbers first by 4, which is again 36 and positive 12I, and then multiply those two numbers by 2i, which is 18I and positive 6I to the second power. But again, since I to the second power is equal to negative 1, we're multiplying a positive 6 with a negative 1, so that's going to simplify to negative 6. And again, we see two real numbers and we see two pure imaginary numbers that we can combine together. So our solution here is going to be 30 plus, oh, look at that, it's also 30I. So 30 plus 30I. 30 is by adding 36 and negative 6, and the 30I is by adding again the 18 and the 12I. And lastly, I cannot forget to do an example like this because I want to avoid people making this mistake. This is not the same as simply raising 6 to the second power and 4I to the second power, okay? This is not the way we do this. This is again mistakes made again that I want to avoid. 6 minus 2I to the second power means we have 6 minus 2I and 6 minus 2I. So this is the way we simplify this. We have two factors of 6 minus 2I. So we can then just use either the box method or the distribution to get our solution. I'm going to just stick with distribution now and multiply both 6 minus 2I first with 6. So that's 36 minus 12I. We're going to then continue multiplying 6 minus 2I with negative 2, which is negative 12I, another negative 12I, and positive 4I to the second power. Now again, because of the I to the second power, this is going to end up becoming negative 4, multiplying a positive 4 with a negative 1. And we can combine that negative 4 with that 36. So we have two real parts, two real numbers here. That could be combined together, which is going to add up to a total of 32. And then we have two pure imaginary parts that could be combined together to give us a total of negative 24i. So here is the solution. Now there's a special case and a special condition when we end up multiplying what are called complex conjugates. Complex conjugates are complex numbers in the form of a plus bi and a minus bi. So the conjugate of a plus bi would be a minus bi. So for example, if I have the complex number of 5 minus 7i, the conjugate of 5 minus 7i would be 5 plus 7i, and vice versa. The conjugate of 5 plus 7i would be 5 minus 7i. So again, these things are conjugates. Now, because the product of complex conjugates is always going to be a round number, there's a shortcut in calculating the product of conjugates. So for example, if I multiply a plus bi with its conjugate, a minus bi, I can get the product by simply getting the a value, squaring it, the b value, squaring it, and then adding them together. So this again only works with multiplying complex conjugates. So for example, here, recognize first that these two numbers, these two complex numbers, are conjugates of each other. 3 minus 4i and 3 plus 4i, conjugates of each other. So to multiply this, let's do it the long way first by using distribution. I'm going to multiply 3 with 3, which is 9, 4 with 3, which is 12. And then multiply 3 and 4 with negative 4 this time, which is going to give us negative 12i this time, and a negative 16i to the second power. Well, again, because of the I, we multiply negative 16 with negative 1, which is going to become positive 16, which lets us add these two numbers together. And because these numbers are opposites of each other, this is going to cancel out. 12 minus 12 is going to equal to 0. So we're only adding 9 and 16, which is going to equal to a total of 25. Now let's use this rule again. Let's use this rule that I wrote right here. I can get the exact same number by simply using this definition here. So here, if I get the value of a, which is going to be 3, and raise it to the second power, get the value of b, which is 4, and raise that to the second power, that's going to add up to this exact same thing. 3 to the second power is 9, and 4 to the second power is 16. And well, 16 plus 9 again is still 25. So we can find the answer a lot quicker instead of using distribution, and just simply square this number, basically multiply this number by itself and the 4 multiply by itself, and then add them those two numbers together. It is always addition, okay? That's what the rule states. It's always going to be addition. You're never going to add two numbers of different signs. You're always going to add up two positive numbers. And that's going to be, again, the real number that you get as a result of multiplying two complex conjugates. So let's do another example. So right here, we'll just use the shortcut here. The value of a is going to be 2. So we're going to simply just get 2, raise it to the second power, and add it with, this is a 1. So 1 to the second power. So 4 and 1 to the second power is 1. So my answer is 5. So you see, we end up with a real number when we multiply these conjugates. Now, this is going to be very helpful and very useful when dividing complex numbers. Because I cannot be in the denominator of a complex number, we have to get rid of it. And there's two ways that we get rid of the I in the denominator. The first method requires us to simply multiply by the pure imaginary unit, not number, unit. And we do that if the denominator is a pure imaginary number. So for example, if it's just basically bi, we multiply the numerator and the denominator by that pure imaginary unit I. However, if the denominator is a complex number, a plus bi, then we multiply the numerator and denominator by the conjugate of that complex number, of that number in the denominator. So for example, here on number 12, notice that we have an I in the denominator, and again, that is not allowed. Because this is a pure imaginary number, the way we get rid of that I is to simply multiply by the imaginary unit. So on the top, we're going to distribute that I to both terms. So it's going to be 28I minus 8I to the second power. Multiplying 4I with I, that's going to give us, again, 4I to the second power. And again, because I to the second power is equal to -1, we're multiplying a -1 with the -8, which is going to become +8. And we're multiplying a -1 with a +4, which is going to be -4. And now, because the imaginary unit I is no longer, I is not in the denominator, we can actually divide these numbers with -4. So now we can divide, and 28I divided by -4, that's -7I, and 8 divided by -4 is -2. And while this is not the standard form of writing a complex number, this is acceptable. The standard form of writing the complex number is to simply switch the two values. So we move the -2 to the front and the -7 to the back, and this would be the answer. This again is still acceptable. This is fine. It's just not written in standard form. Let's do another example. Again, notice that here I again is in the denominator. That's not allowed. So we are going to get rid of that I by, in this situation, multiplying by the conjugate. I can't use just the unit of I because I'm still going to have an I. If I do that, I still have an I in the denominator with a 6. So I end up just simply moving the I over here and making this the opposite. So that's not going to work because we still end up with I in the denominator. So this is going to require us to multiply by the conjugate. So we're going to multiply by 6 minus 2I. So in our numerator, we'll distribute this 5 into both terms. Let's put parentheses so it makes a bit more sense. And we're going to end up with 30 minus 10I. And in the bottom, because we're multiplying conjugates, we can use again that shortcut. So 6 to the second power plus 2 to the second power. Oh, this is I and I squared. I forgot the 5 had an I also. So this is 30I and -10I squared. So in our numerator, we have 30I plus 10, because we're going to multiply a -10 with a -1. And in our denominator, we have 36 plus 4. So adding the 36 and the 4, we end up with 40. So we can simplify this. So we have 30 divided by 40, I, and 10 divided by 40, which simplifies to 3 over 4I and 1 over 4. And if I write this in standard form, it would be written as 1 over 4 plus 3 over 4I. So there's your answer. Just one last example. Again, using the conjugate. So here again, our I is in the bottom, but because we have a complex number, the strategy for this is to multiply by the conjugate. And the conjugate of 2 plus I is 2 minus I. So for the bottom, we're simply going to get 2 and raise it to the second power and add 1 raised to the second power, since we're multiplying again conjugates. However, for the top, we're going to have to use double distribution. So I'm going to first distribute the 7 and multiply 2 and -I by 7. So that's going to be 14 minus 7I. And then I'm going to multiply by 3. So positive 6I and -3I to the second power. So let me write it over here. So we have 14 minus 7I plus 6I. And again, because of the I to the second power, this is going to become positive 3. We have 4 plus 1. In our denominator, 2 squared is 4, 1 squared is 1, and now we can combine like terms. So 3 and 14 are real numbers that could be added together, so that's 17. And since these are pure imaginary values, I can add those together, which adds up to -1 divided by 5. So my answer can be written like this. We can leave our answer written like this since they don't have any common factors, or I could separate this and 15 over 5, which doesn't reduce, and 1 over 5, which doesn't reduce. And of course, because it's subtracting, we still put that minus symbol there. And there's the answer. So there you go. So this again concludes this the notes on how to add, subtract, multiply, and divide complex numbers. Again, thank you for watching. If you do have any questions, do not hesitate to ask. Send me a message on Remind or email. Again, have a great day.